In this video, we will investigate 4 different ways of igniting our favorite gas giant. We've had the technology to do it for decades. Is there a practical reason to do all of this? If Elon Musk is watching, I will say that igniting Jupiter into a star can terraform its moons.
Just a brief refresher on why this is important. I think fundamentally the future is vastly more exciting and interesting if we're a spacefaring civilization and a multi-planet species than if we're not. You want to be inspired by things. You want to wake up in the morning and think the future is going to be great. And that's what being a spacefaring civilization is all about. It's about believing in the future and thinking that the future will be better than the past. And I can't think of anything more exciting than going out there and being among the stars. That's why.
In order to start a thermonuclear reaction, we need to influence at least one of the 3 main components for hydrogen fusion: mass, pressure, and temperature. The most important thing for creating a star is the amount of hydrogen. So here comes plan A: increasing the mass. Astronomers refer to Jupiter as a failed star. Right now, the gas giant does not have enough mass to compress any further. This means that it cannot reach the critical temperature needed for starting hydrogen fusion. How much more massive does Jupiter need to become? 79 times its own mass. So overfeeding Jupiter is out of our current technological capabilities. Moving on to plan B, increasing the pressure. If until this point this video was not crazy enough to subscribe to the channel, listen to this. We can inject Jupiter with a microscopic black hole the size of a human hair. Although the black hole would initially start swallowing some of the mass of the gas giant, the energy and pressure from the formed accretion disk pushing outwards will be equal to the gravitational force pulling material directly inward. This equilibrium is called the Eddington limit. Using a black hole will not start thermonuclear fusion, but looking from the outside, Jupiter will shine and produce heat as a star. Hey CERN, how's it going with creating a black hole? Alright, moving to plan C. What doesn't kill us makes us stronger, said the dinosaurs and evolved into chickens. Our next not so crazy idea is to collide the gas giant with a large enough asteroid. This will increase the pressure and temperature in a specific area. As Jupiter is not solid but made out of gas, the asteroid will just go for a dive. Falling through, heat will be generated from the friction between the asteroid and the hydrogen layers. If accelerated to an ultra high speed, the temperature and pressure will increase enough to start a fusion chain reaction between ordinary hydrogen. Is it easy to find an asteroid for our purpose? Let's ask an expert.
First of all, it happens with or without us, because we are in the shooting path of countless thousands of asteroids and comets. So what you would do is you'd find one that's headed close to us anyway, in the 7th orbit down the line or the 100th orbit down the line, and then you'd slightly deflect it.
Are you saying we have the technology to do it?
We know how to do it, but we know how to do it on paper. The final word is still out on that.
We will revisit this plan in a few years. The last thing we can try is increasing the temperature. We will do what Hollywood does best in blockbuster movies. We will use a several megaton thermonuclear hydrogen warhead. The same approach is already being used on Earth in attempts to create fusion reactors. Instead of compressing hydrogen gas to high pressures, scientists increase the temperature even higher than inside the Sun's core. We can achieve the same effect in the layers of Jupiter by using a thermonuclear hydrogen bomb. It will create temperatures to at least 35 million kelvins. Is it really that simple as detonating a hydrogen bomb? I wish it was. For our fusion chain reaction to start, we need our fuel to be just the right mixture. If the gas clouds of Jupiter contain only pure hydrogen, our bomb would not be enough. Increasing only the temperature will not fuse ordinary hydrogen atoms together. Most elements come in different forms, called isotopes, depending on how many neutrons the nucleus contains. In order to use our nuclear bomb, we need a reaction between deuterium and tritium. It has a higher probability of occurring and releases more energy. The biggest question in this video that you can support by liking and commenting below is how much deuterium Jupiter contains and how deep is it. According to some scientists, large amounts of deuterium are located at a depth of around 50% of Jupiter's radius. The thing we do not know is how rich in deuterium are the layers close to the surface that our bomb can reach. What would happen if we execute our plan? There are 3 possible scenarios. First, Jupiter will explode. If there is enough deuterium, the thermonuclear detonation would cause a rapid and violent chain reaction that will blow up the gas giant. However, this is highly unlikely. If there are such deuterium-enriched areas, they would be located at a depth not accessible to any man-made spacecraft. At our current technological level, we could reach a depth of 5% of Jupiter's radius before imploding. In the second scenario, the detonation produces a fizzle. Some amounts of hydrogen fuse. An enormous quantity of energy is produced, but the temperature and shockwave disperse the surrounding fuel and the reaction cannot propagate in Jupiter's mass. This is highly plausible since nobody tried this before. In a different version of this scenario, a self-sustainable fusion chain reaction is triggered, but only in a limited hydrogen layer. Thus, the planet becomes like one of the hot gas giants discovered in other stellar systems that look like a disco ball. In the last scenario, the hydrogen density around the detonation site and the deuterium concentration are high enough to support a massive explosion. The shockwave presses the underlying fuel towards the planet's core, preventing it from dissipating. The chain reaction propagates in a substantial part of Jupiter and becomes self-sustainable. Obviously, for safety reasons, we should execute our plan only when Earth is as farther away from Jupiter as possible. Our planet can receive trillions of kilograms of hydrogen. Compared to our planet's atmosphere, this is still under 1%. If we time it correctly, we can even use the Sun as a giant umbrella to deflect it. What should we expect to see in our night sky? The brightness of any star is connected to its mass. Being 1000 times less massive than the Sun, we will see an object 6000 times fainter than the Moon. Don't expect a faster tan line on the beach. What about the change in gravity? Wouldn't we experience massive earthquakes or a change in our orbit? Don't worry, that's still a big no on any apocalyptic predictions. As explained by Newton, the gravitational attraction is proportional to the mass of an object. When ignited, the gas giant will lose about 10% of its mass. Being so far from us, there is absolutely nothing to worry about. All of this might sound like science fiction, but bold plans like this are necessary for colonizing the solar system.
I can tell you what I hope the future has, as opposed to maybe what it will be, because this may just be wishful thinking. I hope we are out there on Mars and maybe beyond Mars, the moons of Jupiter, traveling frequently throughout the solar system, preparing for missions to nearby star systems. I think all of this is possible within 50 years. And I think that would be very exciting to do that.